Welcome to Embedded Internals. This is 7th episode of our series Execution Awareness series. Today's topic is memory layout of a Linux program. Today we are going to answer a very or oftenly asked question that how a program runs. When a program runs, how the memory is actually organized inside it. This is a very important topic, and this is where debugging, performance, and system design all connects. Let's see memory layout in a different segments of memory layouts of a Linux program. We have usually five most important segments of a program. So one question which is usually asked, what is segment? Or when I am using the word segment, what it mean and what happened when we crosses that address space. So we can say the process address space consists of virtual memory which is addressable by the process. So like dependent on the architecture, 32 or 64-bit architecture, we have some address spaces. The interval of legal address which can be accessed by that area segments are called memory areas. So legal address are memory areas. When the process, if the process access the memory outside its legal memory area, it will kill the process and causing the segmentation fault. So every memory area is associated with corresponding permission like read, write, and executable, and each segment, like a stack segment, have their own address spaces, start and end address spaces. Similarly, text segments, similarly, heap segment, data segments, everyone has their legal address space. If it crosses their address spaces, then the error will call segmentation fault, or some memory related error will occur, which is very dangerous for the program, and it can kill the process uh, at that time. So we have five segments like stack, shared memory, shared libraries, heap, BSS, data, and text segment. They are from higher addresses grows toward the lower addresses, whereas stack has a property that it grows downward in the address region, whereas heap has the property to grow upward in the memory region. We will check these properties of heap and stack segment from the corresponding memory regions as well. But at this point of time, just understand this table. This is going to be a very important table from developer's perspective. So first thing, who creates and allocate this layout? This particular layout is created by kernel. First thing, kernel is the one who creates this. And when the moment when you replace your process image, execve, when the process image got replaced, this system call is called to replace the process image, and during that time kernel allocates or kernel creates this memory address. Okay, so we need to very much clear that what goes inside which segment. Let me start from the text segment, because heap and stack segment are very important segment and we need to cover that in detail. So I'm starting with text segment first. So any code data which you write or compiled program logic that goes into text segment. Compiled code logic, or we can say machine instructions, that goes to text segment. Few properties of this segment is this is read only, because if the segment not be set as read only, then any process can modify the data of the text segment and our code logic will change. So for the security reason, for the stability reason, this is set as read only, and they are in the executable format. One more thing, the text segment is usually shareable. So at one time, single copy of program code can reside into the virtual address space at a time. It can be shared among multiple processes. And that is the reason process cannot accidentally change it. We are setting that using read only parameter for the security reasons. And then comes the data segment. Data means data segment contain global variables. Let me write it down. Create one segment address and then write data segment. You write as a global variable, when you write int x is equal to 10, so you have initialized this value, it will go into data segment. The properties of data segment is that it has read and write both permission. Read write permission. And the data segment we will find in elf file. Elf file has all the segments. I will show you. And at the starting of the when the program start, all these variables goes into their proper segments. It's not like that it's in the running code get it. Okay, so it contains global variables, that can be global variable as well as static variable that is initialized. And the value of these variable, we know that it is our read only. BSS stands for block start by symbol. Data segment contain initialized variable and BSS contain uninitialized variable. Uninitialized global variables. Okay. Global, anything with extern or globally defined or static. Goes into BSS segment. They are uninitialized, so anything you write as initially int x, so that will go into stack segment. You write a program and in the global area you write simple int x, so that is BSS part. The important thing about the data segment and BSS segment is that data segment are part of ELF file, whereas BSS segment are not stored in file. They are initialized to 0 at runtime. So they are given the variable whichever is initialized, and they are initialized to 0. Zero initialization at runtime. Because initially they are not stored in a file. It saves the disk space because they are not stored in a file. Kernel initialized it. So major difference between stack segment and data segment is that stack segment contain the initialized global variables and the static variables. They have read and write permission and they are stored in a file on the disk. Whereas the BSS segment, which is block start by symbol, contain uninitialized global variables, global or static variables. They are initialized with 0 at the runtime and they are not stored in disk. Therefore, they are not stored in a file. Therefore, they saves the disk space, and initialization like 0 is done by the kernel itself. Now comes the heap segment. Heap segment we have seen. Okay. Heap segment. This is a very important segment. Heap segment means first thing you need to dynamic memory. We have two different type of memories. One is static memory and one is dynamic memory. Static memory is one which is initialized at the compile time, whereas dynamic memory are initialized at the runtime. Dynamic memory are allocated using library calls or system calls malloc, calloc, realloc. Okay, dynamic memory runtime allocation. When we require large number of memory, we usually use heap segment or dynamic memory allocation for initializing a larger value of memory. Dynamically allocated, okay. So function calls are calloc, malloc, and realloc. Sorry, realloc. They are used to allocate the memory dynamically. And there is one free which is used to free the allocated memory by using any of the uh, memory allocation function. Okay, free the memory. So we have three system calls to, or we can say system call, or we can say library functions malloc, calloc, realloc to allocate the memory, whereas we have one free library function to free the allocated memory using this. One of the unique property of heap segment is that it grows upward in the memory region. Upward. And one most important thing is that this is a part of glibc allocator. It is managed by glibc allocator. The difference between calloc, malloc and realloc is that when we allocate the memory using malloc, large chunk of memory is being allocated and the pointer to the first address of the memory is returned by return returned by the malloc function, whereas the memory which are returned by the calloc library function are usually allocated or usually allocated with 0. So memset also is part of calloc. Malloc is just allocation of memory, calloc is allocation of memory, and then set all the memory to 0 so that garbage value is not there. Realloc, when we need to allocate more memory during the runtime of program, we simply call realloc the memory region. So the new either the new memory area has been allocated or some more memory has been added to the already allocated memory address space. So the functions like we can simply call int, they are pointers, so pointer ptr, malloc, size of whatever data type you are using, size of int into how any number of memory you need to allocate, and it return the address. So we to free it, we simply pass the pointer of the allocated memory. So free, this will allocate the memory and this will free the memory. So heap is basically the flexible memory. Anytime you can allocate any number of memory. So this works at runtime. Flexible memory, but It needs manual memory management because most of the error which occurs are during the heap region of the memory segment. Null pointer access or memory address out of the address space, out of the allocated region got accessed. So these kind of error we see at this area. And heaps has lots of problem, like I have already said, some fragmentations. One is so I hope everyone is clear on the heap reason. Heap is a memory segment where dynamic memory allocation happens. We have three system calls for allocation: malloc, calloc, and realloc, and one system call uh, to free the allocated memory. Heap segment provide the flexibility of memory, but it needs the manual management. And the unique behavior of heap segment is that it grows upward and is managed by the glibc allocator. We have some problems or some common errors in the heap region. So heap region errors: either you have not allocated the memory and but forget to free. When you forget to free the allocated memory, forget the free, so lots of memory get allocated but isn't freed. So we have memory leak, which is a very dangerous problem. You have double free, once free and again by accidentally you have freed the pointer. So when the pointer got freed and other time it doesn't know where to free it, either it frees some different memory reasons or cause the problem of double free error, which itself is a cause the system crash or process crash. We also have fragmentation problem. Fragmentation is that as memory we have two type of fragmentation: internal and external. Fragmentation is simply that memory is available inside the system, but uh, the available memory is not in the uh, requested size. Like you need the hundred of into in its size memory, okay, 100 chunks of memory. So we have 25, 35 like this chunks of memory available, but not the continuous block of 100 memories. So memory are available, but the memory are not usable because we cannot allocate that part of memory. Okay, large allocation is there, no? So memory problem can occur. Sometime it happens that uh, large size of memory are so kernel sometimes allocate this type of these, sorry, memories are available but not in the requested region. So like this memory got freed, so kernel cannot allocate these type of memory. So we have memory but not usable because it's available in fragments, it's available in some chunks, not in the uh, detail or not in that large size requested size. So then the problem of internal fragmentation inside memory is not able, or external fragmentation problem occurs in the heap. After the heap segment, let's go to stack segment, most important segment. Like the heap stack segment. Stack segment, we can say that it uh, it get created during the function calls. Whenever you call any function, a corresponding stack will be created. Stack segment contains all the local variable defined inside a function call. is under stack segment. It also contains all the function parameters and the return values, return addresses. Like the heap segment grows upward, stack segment grows downward. Heap segment is managed by glibc allocator, whereas stack segment is self-managed. Self-managed, or we can say automatic managed. Self is not a word. Let's take automatic managed. Usually we allocate small size of memory using stack, small memory size, because stack has limited size ability. When we allocate large allocation, when we do the large allocation at the stack, we might face the problem like stack overflow or some these kind of problem. So example of this, like you have created a function void add. Inside that you have two variables, int a and b and c also. So a b c, all those will go on stack segment, yes. And you are doing something a or b is equal to a or b, and return address will also be stored in the stack segment. So variable defined inside this function call all will go into the stack segment along with the return address. So we can say stack is fast because lots of memory allocation is being done at stack, but it has the problem of size. So small memory size but fastest execution. Fast execution but small memory size. Already have explained that stack has some problem, like we have stack overflow problem because stack is usually limited memory. So when we allocate memory larger than the stack segment, we face the problem of stack overflow. Like in the recursion calls, we see that same function has been called again and again, and then at that time stack overflow occurs. Stack overflow is a common problem, we usually see this. So we need to be very careful while allocating the memory variables inside the stack segment, so that that should be in the memory region or recursion limits also. Problems or error occur at the stack segment. Stack segment. Latest, there is one more reason we have defined in the memory layout, that is shared library reason. Shared libraries reason. I will show you again in the this is shared library reason. Okay. Now the library like libc, dynamic linkers and other .so files are included in this shared library reason. So code is shared between process and it saves the memory. Therefore, we have an reason inside the kernel layout, so that memory is being saved. And shared library, so what it contains? It contains libc and dynamic linker and any .so files. And this area is loaded via ld linux, that is dynamic linker linux.so. Okay. One more thing is that is very important concept is the concept of virtual memory. We all know that RAM has limited size. Any embedded device has very, very limited size. Size is always a issue, or memory is a very critical resource which needs to be properly managed and shared among multiple processes. But by the concept of virtual memory, we create an illusion for the process that we have sufficient memory, or we can say all the memories of the system or the operating system go is directly owned by the process. So process don't know that the actual memory it is using is very less. It sees that whole memory belongs to them. It's the task of kernel to manage the memory efficiently without the user or without the process being known that it has a limited memory access. So virtual memory is actually a illusion concept to the process. Process is an illusion that it owns such a large chunk of memory. So what process sees is like 0 into 0 0 0 0 0, starting to this to the highest address 0 into all memory belongs to one process. This illusion comes under a memory which is called as virtual memory. They are not actual memory, but the virtual memory which a process owns, not the actual RAM or physical memory. And the kernel or memory management unit MMU is the one who manages this virtual memory translation. Okay, so it is managed by kernel unit, memory management unit, so that each process gets the sufficient memory with sufficient memory and illusion that okay, whole memory belongs to you, use the memory as you want. But actually uh, it's not true. Each process thinks its own full memory, but this is the concept of virtual memory. It owns the virtual memory, not the real RAM memory. Okay, so lots of talk. Let's go to the coding part. Let us do some coding as well now. Okay, we have created one program. I will explain you the code first. stdio.h. This header file is included for printf and scanf statements. Okay, for printer scan. stdlib.h. This header file is included for dynamic memory allocation functions. These two are the global variables. One is initialized and other is initialized. Both initialized global variable goes into data segment. So I have written global where in for initialized with the value 10, and it shows that it will go into data section. And we already know that uninitialized global variables goes into BSS segment. Then comes the main function, where we have returned a statement, hello world, welcome to episode 7 of execution awareness series. And we have created some heap variable like local variable which has a value 20. It is a stack segment. It will go into stack segment as this is the part of local variable of the function main. We have dynamically allocated memory in the heap region by using malloc function, so that will go into the heap segment. I have printed the addresses of the all these. So main data segment, data address, what's the value, what's the address, similarly BSS and stack and heap segment. I hope the simple code is clear to everyone. Let me run it. GCC hello world.c hello world. This creates the ELF file. Okay. When we run hello world, we have the addresses. See, data segment has global variable 10. Mark the address 18. Similarly, BSS 18. So 10 to 18, it's increasing. Local variable stack segment is an upper region, so it is 7 FFDC, a higher value range, whereas heap segment is at lower value range, so it is similar to data segment but 590 it in lower range. When you run the program again, observe one thing. 31C addresses of heap segment 590.155.90, and then it goes to B address, so it is growing upward region. Okay, first 9 then B stand for 11. Okay, similarly when we see the stack segment 7FF DC and EE, this address 31C shows that it is going in the downward region. Okay, initially FF value, then E value, then C value, lower addresses region. I will show that how we can check that memory stack and heap memory goes from upward and downward direction. I will just run this program using some wait state. Okay, wait state I am using so that in the meanwhile we can check the procs function, proc files. Okay, so let's compile it. We have one warning. Let us fix this warning. This needs an header file, so we will include one header file, that is hash include unistd.h. This is to include sleep. No errors, no compilation error. Okay. Dot slash hello world. This is running and waiting for the program. In the meanwhile, let us check the address PID of this. Process ID is 3784. Let me go to this area slash proc 3784, and we need to check the memory mapping. So maps. Okay, we have stack. See the range of stack. Okay, and similarly I will show you the heap segment. See the range of heap segment. Heap is growing upward from 9315 to 80 this 0, whereas when you check the stack segment you will see the downward properties is being seen in the memory region. Okay, this also you can see the size of text segment is 323, data segment is this, and BSS segment is just 12, whereas data and BSS both contain one global variable only, but BSS segment is so contains such a small size, whereas data segment is of large size, because BSS is not stored in file. Variable defined in this area is not stored in file, therefore it saves the disk space. This is the proof we are saying about BSS. Okay. Let us check the memory. Text has two memory protection, R and X, that is read and executable permission. Data has read write permission. Heap has read write permission. Stack also has heap read write permission. Only the text segment is read and executable permission. The permissions are like this, so that the memory cannot be accidentally accessed or modified, or unauthorized access can be provided. One very important area, or usually asked interview question, is what's the difference between stack and heap. So first thing, we have seen that stack grows downward, whereas heap grows upward. In the stack we has automatic allocation, whereas in the mean we have in the heap we have manual allocation. Stack is usually limited size, uh, page size, or whereas heap there is large size of memory can be allocated. Stack has function scope and is usually very fast, whereas heap is slower in execution, and it is available until we call the free system call. So memory once allocated is available till the free is called. Say that memory is not random, it is carefully structured and protected resource by the operating system. You need to remember that when a program got loaded into the kernel allocates some memory which is divided into several regions, which we have seen. These are the different memory regions of a this is the different regions in which memory is being divided. Each region has a specific purpose as well as specific permissions. Why? So that kernel CPU can access the memory safely via virtual addressing. What is virtual addressing? We have already defined. Virtual address is an illusion by of a process that all the memory of a system actually belongs to it. That but in reality it's not true. So that we have virtual addressing, CPU access the memory safely. This is the scope of today's episode. We can say that memory is structured, virtualized and protected per resources by operating system. uh, it is a very by operating system. In the next episode we are going to cover user space versus kernel space. In that episode, we are going to see system calls in depth, mode switching, how the printf or any system call works or reaches till the hardware, and what are the securities boundaries of user space and kernel space, which is going to be in detail, depth detail. Please stay tuned for same. Thank you. Thank you so much.